Hello. So I wanted to start this series for people who are interested in chemistry in any kind of way. I want these videos to be able to help a high school chemistry, honors, regular, or even a AP chemistry student. So a high school student who's just learning chemistry for the first time or is taking their second year in AP chemistry. I want this kind of to be perfect for a high school student, also perfect for a college student studying chemistry, or someone who is not learning chemistry in a classroom at all, but just wanted to learn chemistry and wants to learn the scientific complexities and feel a lot more knowledgeable on subject material discipline that might be hard and really just make it really simple and make it fun to learn and show that anyone really who puts their mind to it can learn the complicated world of chemistry. So I just want anyone to feel they can learn chemistry, feel more knowledgeable. So young students, old students, these videos are going to be perfect. People in school or out of school. And I just wanted this to be taught in a really engaging, but also relaxed kind of setting because there's no grade. Also, I think I have a lot to benefit here because I think for me, it's going to be nice. I'm going to get to learn a lot in this series on how to teach in a digital setting because I've taught a lot person to person or in a classroom as a TA. So, and I hope to develop a connection with the audience and offer tutoring for anyone interested. I'm going to leave my contact in the description. I studied chemistry at a university in Atlanta. So, for just an undergrad. And so I have my contact information in the description, the bio. And it's going to be, it can be free for anyone who's interested. And because I love teaching. So I think it'd be really good for anyone interested. So today I wanted to introduce us to the entire field of chemistry, but I don't want this series to be a complete chemistry intro course because I believe most people over the age of 16, we usually get some kind of intro to chemistry in a high school setting. We've learned bits and pieces since elementary about what's an electron, what's a proton, what's a neutron. And so I think this is going to be a little more mature and going to get us really into more interesting aspects of it. Even someone who knows all this chemistry, I'm going to add a lot of history and interesting knowledge that'll keep you engaged and teach you something you didn't know. So we learn about the elements: boron, carbon, nitrogen, oxygen, fluoride, down to bromine and francium, titanium, vanadium, metals, nonmetals, semi-metals. And we learn that every atom has a symbol to represent it. So C is for carbon. And when we say C is for carbon, we are talking about an atom that has 6 protons in the very center and typically has, sometimes a little more, 6 neutrons or neutral building blocks within the nucleus. And then it also has 6 electrons in its ground state. So that's when it's not ionized in any way. That's kind of naturally how it occurs. But of course, carbon doesn't just behave as an atom very often. It either will want to bond with other carbons, usually having 4 carbon bonds, and it can make crystals like diamonds are carbon crystals, or graphite. We have buckyballs. And we also know carbon is in everything. There's carbon in life. So every living creature, every atom that is life, every well, I shouldn't say atom, every cell that has any life into it, everything that's living usually has, almost every time we've observed, has carbon in it. And so we learn about this in chemistry. So it's organic chemistry is usually the study of carbon chemistry, but it gets a little complicated because we have carbon molecules like carbon dioxide that technically aren't considered organic, but they're called, even though it has carbon, so it gets complicated. But we've learned a lot about this stuff in intro chemistry. We learn about grams and moles and stoichiometry, and those are all topics that I can address in another video or one-on-one if you're interested in trying to grasp those topics. But I believe a majority of the people watching this have some knowledge, and there's going to be a wide range. So I'm just going to try to teach in a way that's simple, and you can just skip past the parts where I'm explaining topics you understand. But I want to add some cool history. So, uh, yeah, let's do this very casual. And eventually, I hope these videos will have a visual aspect to it. So, we look you look up ketone or aldehyde chemistry, and there will be a professor or a tutor. They may have a webcam, they may not. They usually almost always have a black screen that is drawing out and representing whatever chemical they're talking about, whatever reaction. And so I think that that'll be something I'd love to implement for some videos, and but it doesn't have to be. Also, um, I know sometimes some of the words chemists say when people are teaching chemistry, they gloss over and don't address what that word was. You'll hear a word like alkoxide. You'll hear a word like imine, amine, amide, azole. And you just kind of sit there and think, oh, okay, what did he say? What did the person say? And how do you spell that? So I'm going to try and spell out words that are not, that are new to someone. So, like for instance, carbonyl, and leave that in the video as a subtitle. Um, so today for this first uh, lesson, I just wanted to go over Lewis structures. Lewis, you hear them called Lewis dot structures or Lewis structures, are just a way to represent atoms or molecules on paper to reflect their atomic nature. So that's kind of the joy of chemistry, is taking these really small atoms and these molecules and complicated things they do, and we try to symbolize it on paper in a universal language that somewhere on the western part of America, to someone in England, to someone in India or China or Japan can learn and know what we're talking about and what has been discovered. So Lewis structure. Lewis structure is named after a man called Gilbert N. Lewis, or Gilbert Newton Lewis. Gilbert Newton Lewis was born in Massachusetts around 1875, and he went on to study chemistry and was a physical chemist. But he did his work up until the year of 1946 when he passed away. Um, so he lived in the early 1900s doing a lot of work. He specifically was notable for his study of chemistry at specifically UC Berkeley. UC Berkeley is just a college that has so much history with chemistry because they founded so many different elements and were so groundbreaking. So that's where he worked. He received his PhD from Harvard and was just a very renowned chemist. Gilbert and Lewis laid a lot of the foundational groundwork for what is chemical bonding, what is covalent bonding. He's a figure in chemistry very much like Linus Pauling. And so you'll hear his name come up a lot, Lewis, when we are learning terms in chemistry. So Gilbert and Lewis, he goes on to tell us about concepts of like acids and bases and defines them, and that's where we get the term Lewis acid and Lewis base. So let's jump right into it and let's see what a Lewis structure looks like. So a Lewis structure is just there's a few steps to it, but a Lewis structure is going to look something like this. Someone will say, draw a Lewis structure of a hydrogen atom, and it's ground state, it's unionized, just atomic hydrogen, and you'll draw it like that, just an H to represent hydrogen, and it's one electron it comes with. And so hydrogen gas does not look like this. It doesn't, first of all, atoms don't look like H's. Uh, they are more spherical and moving constantly, but how they actually occur is hydrogen gas is H2. So these are representing two hydrogen atoms, and each one of them has one proton in them, and the amount of neutrons varies. It can have one, it can have two, but it's going to have one electron kind of circling around at high speeds and around the nucleus. But when there's two hydrogen atoms together, they're going to share their electrons together. Kind of looking like that. See the two minuses, there's a plus here, because those electrons, they like to pair up. Electrons, that's just a trait of electrons. They like to pair up, and they often um, will share an opposite spin, but not to go too much into that. So that's a Lewis structure. It's symbolizing this and this. It's symbolizing a hydrogen together. So when someone says draw an H2 Lewis structure, two hydrogens, hydrogen gas, it's going to look like that. And that's going to be your answer. So I want us to look at another example, oxygen. If someone said on a test or in class, or you just wanted to symbolize oxygen, atomic oxygen, so an atom of oxygen, one single atom, you have to, and we will be able to look at a periodic table of elements and reference it in another video, but you have to know how many electrons are gonna be in the atom of oxygen. And the answer is going to be six. So there's going to be six valence electrons. So there's the O, you draw the O, and then you simply draw six, two on top. It doesn't matter how really you draw them too much, as long as you're pairing them up and filling it out. Two, four, six. Not where the blanks are, doesn't matter. I could have drawn it like that. That's an acceptable answer, or I could have drawn it like that. So they're just paired up. Um, it's not good to, if you draw it, to draw it like that. You want to avoid drawing it like that because then it appears like it has two radicals. So see how those electrons are on their own. So these valence electrons. So those valence electrons are representing the electrons that are going to chemically react because it's only the outer shell electrons that really are doing the reacting and the bonding with other atoms and their nucleus and their atoms and making these orbitals and bonding orbitals. So um, we're going to, there we saw oxygen. And the steps to doing a Lewis structure is you have to, one, determine the connectivity of the atoms in the molecule. So basically, you have to find out what is the central atom. The central atom usually ends up being the least electronegative because generally speaking, less electronegative atoms are more likely to have multiple bonds because they don't mind sharing their electrons, like carbon, for instance, like nitrogen in some cases, you know, whereas the halogen, so chlorine, bromine, fluorine, they are far more likely to just be on the outside and not a central atom. So you got to learn how to know how many valence electrons there are. So that's kind of understood from just knowing the periodic table of elements and knowing there's a way to symbolize it, and you have to just kind of know eventually and have it memorized. But oxygen has generally six valence electrons. Hydrogen is going to have one on its own, but you'll grow familiar with that just by practicing and knowing the periodic table of elements. Basically, every row shows you how many valence electrons it has. So everything in the row of hydrogen generally starts with one. So you're looking at potassium and all the other elements below it. And then calcium starts with two. Then you have the D block of metals, which gets a little more complicated, but you can technically think about it as kind of having three if you want to think about it that way. But it's a little more complicated. Boron and the boron group is going to have three, carbon four, nitrogen five, nitrogen group, oxygen six, fluoride, so the halogen seven, and then noble gases will be eight. They'll have a filled octet. So the once you understand that and you add the valence electrons to the molecule, you'll be able to fill each atom's octet. And what that means is you want every atom to basically reach eight. I say basically because there are some unique cases, but generally speaking, hydrogen and helium, they just need two electrons because the smallest atoms, the S block, 1s1, 1s2, they only need two atoms and it's like filling an octet. Um, Whereas when you get into the medium-sized atoms, carbon, nitrogen, oxygen, fluoride, phosphorus, generally they want to have eight electrons in their valence electrons in their perimeter. So let's see what that looks like. Let's do another example. Let's try drawing methane. So methane is also known as CH4, carbon, tetrahydrogen, CH4. So that's going to look like this in a Lewis structure. It's going to be really, really easy. You're going to draw C as the central atom, C, and you just draw four hydrogens going out from the center, connecting to it, indicating that they're bonded together. And that's all you need. That's the methane's Lewis structure. Now, let's try chlorine. Chlorine, atomic chlorine. So someone says, show me the Lewis structure from chlorine. You're going to draw out the symbol for chlorine, Cl. You're going to write it out, Cl. And you're going to draw 7 electrons. Okay. And you have your answer. Now, chlorine often will be ionized as chloride. So, in Lewis structures, sometimes they will add a plus or minus. And to just simplify things, all that means is you take what it would have been in its neutral state, what it would have came with its electrons, and you add or take away that many electrons. So if it's Cl minus, because electrons have a negative charge, that means it just gained 1 electron. If it was 2 minus, it meant it gained 2. 3 minus, it would have meant it gained 3. If it's plus, it means the Lewis structure is missing 1 electron. So, so let's draw Cl minus or chloride, ionic chloride. It's often how chlorine appears as Cl minus. So Cl minus is going to look like this. And I wrote the little minus symbol up there to represent its negative state. It's negative because there are more electrons than there are protons in chlorine right now. So because it was given an extra electron, which can happen, for instance, in the presence of sodium, and that's how we have sodium chloride salt, which dissolves in water. So let's draw sodium. Sodium is symbolized elementally as Na. And if you're remembering, the symbol for Na is that the actual symbol for sodium is not applicable because for whatever reason, instead of it being SO or whatever, Na, it's not applicable or doesn't make any sense. Um, so that's one little way from sodium, Na. For instance, there's another one, tungsten. W for tungsten is symbolized by the wrong. That's a little my little mnemonic for remembering. So Na, sodium. Atomic sodium starts with 1 valence electron. Of course, it has many other electrons in its inner shell, but for intensive purposes, it has 1 valence electron. And in the presence of chlorine, it ionizes or gains a charge. And to sodium becomes a plus ion. So that means to gain a plus charge, it would have to have 1 fewer electrons than it has right now to make an imbalance. So that would be 2 Na plus. You see, it has no valence electrons. It's lost its only valence electron, so it has nothing. And that's where we usually find stable atoms in a Lewis structure. When we're just drawing single individual atoms, it's either going to be um, at 8 or at 0. That's generally what you're going to end up having when it's ionizing. That's usually where a lot of atoms are thermostable. And that's when they have ionic bonds, which just means they lose or gain an electron. Um, I guess the final one we can draw is going to be formaldehyde. So formaldehyde is this. Please remember. Carbon double bonded to oxygen with two hydrogens. And that is the Lewis structure. So just to recap what we learned today, uh, we learned about Lewis structures, and this is an excellent introduction to organic chemistry because organic chemistry and chemistry as a whole is all about representing what is happening chemically on the atomic scale, where we're talking about angstroms, we're talking about nanometers. It's about representing that on a piece of paper in formula and representation. So Lewis structure is a way to represent atoms and molecules with their bonds and with their lone pairs of electrons. And we learn about who was Lewis, and we'll learn more about him and his other theories when it comes to Lewis bases and Lewis acids, which are also more centered on the electron aspect of it, whereas Bronsted acids and bases are more emphasized on the hydrogen aspect of it. So that's going to conclude today's video. I know this was really long, but I was glad to make this. Thank you very much.